Okay, so yesterday I was working. Well, yesterday I was looking into this sort of zkLib library, um, and basically I got sidetracked and started doing Mathlib pull requests. So maybe I'm going to sort of start today and try to go in the opposite direction and look at some of the pull requests, and then maybe if I can sort of move those forward, go back to sort of learning about this zkLib. Um, So let's see, what are the status of my pull request that I opened yesterday? I think I saw that there was, yeah, so there's a comment on least one. So this is the main one that I was working on yesterday about this sort of polynomial lemma. Looks like it's sort of in a working order. One thing that I can also do is I can use this sort of keyboard thing to like make sure that it's in like a ready to review status. Keyboard lean. Of course, it doesn't show up. Perhaps I can log in GitHub here to zkLib, and I want to search for keyboard to actually find the website where it is. Okay, so these are like links to keyboard, so surely this is, oh no, this is links to the GitHub page for keyboard. Does there a link to the keyboard itself? Okay, cool, here it is. Probably I should like make some sort of bookmark. Is it Command D like it is in Chrome? Yes, I'm just gonna call it keyboard. Into the bookmarks toolbar. Save. Okay, cool. And I just want to make sure that this 22847 is present. And I think there's, yes. Why is my PR not on the queue? So you can check to see that your PR is on the queue. And sorry, what did I say the number was? 22847. So if I sort going down, 228, it's probably going to be 2286, 228. Yeah, okay, cool. Yeah, okay, wonderful. But so both of them are awaiting review. So that's good. They have this green check mark. But this one, so this one in particular probably will take some time because it's not necessarily a tech debt one. I think the tech debt ones are sort of, the review process is a bit streamlined. Whereas this one, you know, is going to take the normal process of someone looking at it. It's like a new feature, so someone has to look at the lemma and make sure that it looks good. So that's fine. And I can maybe go to this one. So this is one that I hadn't really covered when I was talking about it yesterday, but this is just some lemma. So there's this doc prime linter, right? There's this doc prime linter. Basically, a whole bunch of lemmas in Mathlib have these primes after their names because there's like a similarly named lemma, and it's just not a very good way of naming things because you don't know what the primes mean. And so we're trying to sort of get rid of those. And in this case, I have been trying to get rid of one. And I see that I have like lots of comments, but basically this one was previously named with like 3 primes, and so I renamed it. And I also changed some other things to just sort of make it a bit cleaner. And so I see Eric has reviewed things, so let me go and look at his suggestion. Okay, suggestion number 1, add the line at a lab as a limb. Right, so I'm inclined somewhat to just, yeah, I don't really like know what this is, but I'm being told to do it, so I guess I'll do it. Maybe I should like find out what it is. Maybe I can like, okay, I'm just gonna commit this suggestion here. And then when I go and pull it, maybe I can sort of look into what actually it is, this lab as a limb thing. I think it's something specifically for induction lemmas. Okay, second suggestion, can you rename these to C and monomial add right? So I think he's saying that I should rename the variable name here so that it works with induction. Yeah, so I saw this. I wasn't sure if he meant that like there's some reason it can't be used with induction if it's not named in a very specific way. But maybe I can go and make this changed here. I can also like increase the size of the font. And I can increase font size here too. Okay, so let me sync to get the change that was made. Yes, so this a lab is a limb. What is this? Right, but of course mousing over it doesn't tell you a collection of modifiers on a declaration. Yes, but is there a way of seeing a docstring for what a lab as a limb itself is? That seems like a problem with this sort of mouse over thing. I just want like, what happens if I like search for it? Like, is it such a thing as actually has a docstring? Okay, 430 results. Right. Is there a result where it like is immediately followed by a space? Yeah. I worry that it's defined somewhere in like the elsewhere in the stack here. Let me see if I can go back here and like try and find like lean reference. Yeah, okay. New manual for Lean 4, thank you. Will this work? Lab as limb. No search results. Yeah, what if I go to like the docs? Docs for. Yeah, of course, this is not. Okay, this is something that I also need to create like a Mathlib for docs. This is what I want. And can I like create a bookmark for this? Docs for save. Cool. And I also want to like continually see the bookmark. Okay, but can I like search for this? Apparently not. What happens if I like search for like, can somebody like in the Lean 4 describe it for me? What is a lab as a limb? Yes, please just, is there any way of finding what the documentation for this thing is so that I can actually understand what I'm being asked to do? Right, lab as a limb. I mean, the main thing is just I want to like mouse over an attribute and have a description of what that attribute is. Lab as a limb, a lab as a limb. Right, so like lots of references to it, but no like actual description of where it's defined. Okay, well, this is not too important, so I'm not going to spend too many more minutes on it, but it's just a sort of dumb thing. Like, I'm mousing over it, where's the documentation for it? Okay, so I'm also being asked to rename things. Okay, so let's do this renaming thing. And I should probably also do it for the nearby ones. Right, so this is like some induction on monomial thing. So presumably I should rename it for all of its friends as well. Right, so, and this is a similarly named one. So what was the naming suggestion? The naming suggestion is monomial add. Monomial add week. Okay, cool. We'll go with that. So this is the like condition where I say that I can add monomials. So this is what I will call that. And then this is also a very similar condition in this induction principle. And the other suggestion was that I should call them like C, just C. Okay, so I'll call it C. And I will call this one C. And do I have another one? Right, so this one, right, so you wanted me to get rid of the H's in front of them, but I could also be doing that here, right? So C, monomial add week, it works with induction, okay? I guess this one is, so if this one is C, okay, can I just like put them on, I'm gonna do like a semantic line break here. I'm just gonna like put them all here so that I can actually like read what's going on. Great. So here I have C monomial add week, C monomial add week. And that's all I need. Here I need this multiplication. So I'm gonna call this mul x. I think that's the correct naming pattern there. And But yeah, apparently it's not present here. I guess it's not needed here. But I guess I should do the same thing down here because it's basically very similar. So C, add, and molx. So I think this should be called C. Sorry, this should be called C. This one should be called add. This one should be called molx. Yep, so I think that's fine. Oh, and I'm being told there's an error down here. Right. This is so presumably the fact is that I renamed everything and now I have to go and make all of the induction things different. Add and molx. Okay, so this is going to change things. Cool. Now the issue is that when I recompile this, it's going to like cause this error to arise if anywhere any one of these induction principles is used. But I guess that's okay. And right, for good measure, this is like another similar one with C and molx. So I'm just going to change this to C and molx for consistent naming. Right, cool. All right, so I think that fixes that issue. Of course, it will like introduce bugs of some kind later down the line, but we can let the continuous integration inform us of those. So this is rename variables, commit, sync. Okay, so I've done that, cool. And then he is asking me to deprime. Okay, so this is if I copy this. So basically he's saying that instead he's saying not to deprime this, but to deprime this to make it so that induction. Is this it? Sorry. Yeah, this is it. So line number 731. Right, so what happens is restart this file because I have recently made a change. Warning, has local changes. Is it going to take forever to recompile? That's an interesting question. Basically, what I'm being told is that instead of induction prime, I should be using induction p with, or induction p using this with, and then instead of like using all the variable names out here, I change it to, right. So, I mean, just to like very quickly remind myself of everything that's going on here. We have C monomial add weak. So if I delete this, the point is that this should be a C and this one should be, yeah, monomial add weak. Okay, let me like, how did this look at the start? A, B, F. Yeah, so clearly it should be like CA or something like that. But the other one should be something like A, B, F, H, A, space I. Monomial add weak. A, B, F, H, A, space H. Something like this. Okay, does that successfully compile? Yeah, okay, cool. And I guess everything is happy. And I guess I simply like put everything in the correct location. Okay, cool. That seems fine. So now I can say I fixed this. D prime induction. Synchronize changes. Okay, so that's accomplished now, and I can resolve this conversation. And so now it will rebuild things and tell me, presumably, if there's any issue. Okay, cool. That seems fine. Thinking that I'm okay with maybe leaving Mathlib for now and trying to return to this zkLib thing and trying to understand it. I mean, maybe the first thing I should do is check and see if anything has happened with the pull request I submitted here. zkLib. I don't know that anything will have. Suggestion successfully applied. What does that mean? Okay, weird. I don't think that, yeah, nothing has necessarily happened here, but that's okay. Mostly I just want to sort of understand. So yeah, to back up, what is zkLib? Here, let me like close some of these other tabs. Signed in with another thing. Okay, right. Formally verified cryptographic proof systems. So basically, what is this? The goal is to formally verify snarks based on IOPs. And they're formalizing these oracle reductions. So this is like one sort of formalism of how the proof for IOPs can be carried through. Aim to formalize Planck and Fry. Some check Spartan Ligero. Merkle Trees is vector commitments and do the BCS transform. Cool. These are all like classic protocols. We aim to provide a specification based on Mathlib polynomials. Implementation using computable representation of polynomials, yes. And then proofs of completeness and round-by-round knowledge soundness for the specification, and proofs that the implementations refine the specifications. Right. At the core of our library, right, this is maybe the part that I want to understand the most, which is this oracle reduction aspect. So the core of the library is this F interactive oracle reductions, right, C oracle reduction. Yeah, always good to do this. In fact, okay, well, it's just a like so I can find it over here. In fact, oracle reduction basic, right? Interactive oracle reductions. An FIOR, right? So what is F? Of course, F is the parameterization. Is an interactive protocol between prover and verifier to reduce relation R1 to another relation R2. Yeah, sure. So in the mode of like a folding or something else like that. Verifier may not see the messages sent by the prover in the clear, but can make oracle queries to these messages. Yeah. It can compose multiple FIORs with compatible relations, allowing us to build protocols. It can also carry out BCS. Using the theory of FIOR, we then formalize various systems in proof system, which is another subdirectory. And there's Spartan and some check, so a bunch of different proof systems there. Okay, so maybe it's good to just like read the basic. Define public coin interactive oracle reductions. This is an interactive protocol between a prover and a verifier with the following format. At the beginning, the prover and the verifier both hold a public statement X and some public parameters. Yes, the prover may also hold private state W. In each round, the verifier sends some challenges, the prover sends back responses, the verifier outputs a decision. Right, so protocol spec. Type signature for an interactive protocol with N messages exchanged. Direction. Okay, so basically this is us building things up, right? So we have a direction. So is it going verifier to prover or prover to verifier? Yes, so those are the two directions that something can go, and I can get things out of these. Sure. The type of the ith message in a protocol call specification. Message. Yeah, so we have a index over like types, protocol spec. So the protocol spec includes the type of the message. And we have transcripts and full transcripts, and presumably that will make it possible to carry out like the Fiat-Shamir transform later. Notation for the type signature of an interactive protocol. P something V, prover state, prover round, prover out, prover, verifier, oracle prover, oracle verifier. Yeah, they can do like an interactive reduction. Okay, so I wonder if there are like examples of this. So for example, just like commitment scheme. Okay, so this like would be interesting maybe to take a look at the Merkle tree implementation to understand how it works. Okay, so there's some sorries though, so maybe this is something to take with a grain of salt for now. Oracle spec. Find the domain and range of the single oracle needed for constructing a Merkle tree with elements for some type alpha. We may instantiate alpha with bit back n or fin 2 to the n. Oracle spec. Right, so this is of interest as well. And this is, right, so this is importing VCVIO, which is this other library. So maybe that's like another thing to pull up here. Okay, here it is in the lean reservoir. Right, so formally verified cryptography proofs in lean 4. This library, so this is like a separate library, but one on which the zk stuff is being built. Provide a foundational framework in lean for reasoning about cryptographic protocols in the computational model. The core part of the framework provides monadic syntax for representing computations with oracle access, with probabilistic computations, denotational semantics for assigning probability distributions, operational semantics for implementing simulating behavior of computations oracles. Okay, so I can presumably I can just follow the link into the Lake packages directory, and I can see something. Right, crypto foundations, asymptotics, hardness. Right. Okay. Cool. Okay, so how is this used by the Merkle tree stuff? So Oracle spec unit. So Oracle spec, let's try and like understand the Oracle spec type. Oracle spec I, a structure, right? So in this case, we're calling it with units. So this is just an empty indexing type. And so the spec is sort of trivial. A structure represents a specification of oracles available to a computation. Available oracles are all indexed by some indexing set. Okay, no, sorry, it's not trivial, it's unit. The unit type has one element. So there's a single element here. So let me see. All right, so Oracle spec is of type unit, and it is the function that returns, right, Oracle spec alpha, okay. Yes, of course there's a variable here, which is being otherwise hidden. Oracle spec alpha is the function that takes a unit and returns alpha, prod alpha, comma alpha. Sorry, let me click on the right thing here. So yeah, the first type is alpha prod alpha, and the second type is alpha. So this is like the input and output types of the hash function. Because if we're talking about a Merkle tree, like what is the modality of using the hash function in a Merkle tree? It's I have two hashes and I need to combine them typically. So here I'm doing that with alpha, right? So like the input type is alpha, and this is also what's sort of commented out here. The domain is alpha times alpha, and the range is alpha. Yes. So that makes sense. Yeah, a Merkle tree with elements of some type alpha. Okay, cool. Lemma domain def. Oracle spec alpha dot domain is this. Oracle spec range is alpha. By Raffle, yes. So these are all simplification lemmas, cool. And now we're going to say that alpha is decidable, inhabited, and fin type. Cool. I'm okay with that as well. Example: a single hash computation. Def single hash. Left A, right alpha. Oracle comp, Oracle spec alpha alpha. Remind me what Oracle comp is. Oracle comp represents computations with Oracle access to oracles in spec. Right. So single hash is a computation matching the spec of the hash function, which combines two alphas into one. And the final return type is alpha. Yes, naturally. And so the computation is I take the left and the right and I evaluate, right? So let out equals query, right? So query the oracle. Query, this is the unit. And we're going to query that on left comma right, and that out will be the output, and then I can return out. Okay, cool. Seems sensible for a single hash. Cache for Merkle tree, indexed by J of type fin n plus 1. What is this? Right, J. Okay, so it's a type, right? The cache is the type of functions from indices to vectors. Okay. Right, so presumably these are like the levels of the tree or something like that. Like index 0 is at level 0. Add a base layer to the cache. Cache.cons. Yes, okay, yeah, makes perfect sense, right? So J is the layer, right? Right, yes, this makes sense. So just to clarify, a cache n is a list, not a list, but a it is a tuple, right? So like usually like functions from Fin are described as tuples in Lean, or that's how we call tuples. So it is an n tuple, no, it is an n plus 1 tuple of vectors of exponentially increasing length. So the first vector in the tuple has a length 2 to the 0, which is 1. So the first vector in the tuple has length 1. The second vector in the tuple has length 2. The third vector in the tuple has length 4. Actually, I should be like talking about this in zero indexing, right? So the 0th vector in the tuple has length 1. This first vector in the tuple has length 2. The third vector in the tuple has length 4. The second vector in the tuple has length 4, and so on and so forth. And so it's a cache. So I can add a base layer to the cache, right? So cache.cons, right? So what's going on here exactly? So if I have an n and I have a list of leaves and I have a cache, then I can, how exactly is this working? So I already have a cache, which is a vectors of all these alphas, these layered vectors of all the alphas, and I have n layers, and I have a vector of the appropriate next length, I believe. Wait just a sec. Right, so the last, this is a cache of length n, and so the biggest j is n minus, is n itself, so it's to the n. So the last layer of this cache is of size 2 to the n, and here we have a vector of size 2 to the n plus 1. And now I'm supposed to be giving a cache, but I'm not just appending it onto the end, am I? Fin.reverse induction. Okay, so this is some induction principle. Let me see. Last cast. So last is leaves. So I think the last thing is just going to be the leaves, right? And what exactly is going on over here? Is the issue that we don't have like a snock? Like is the thing that, let me just quickly look up something. Docs for, do we have tuple snock? Or do we have like snock of any kind? Are they even called tuples? Like fin cons. Okay, we have that. Do we have fin snock? We do. Adding an element at the end of an n tuple to get an n plus 1 tuple. So I wonder, I'm a bit confused maybe why, like, can I just, is this editable by me? Yeah, so this, yeah, we're not in the snock. Application type mismatch. Okay, so presumably the thing is going to be some like weird thing with the type. It makes it a problem. No, there's an extra thing here. What is the issue? Sorry, yeah, because this is this, but can I just do cache? Is that possible? Okay, well it type checks. And apparently nothing else in the file breaks. So I wonder if that's a possible alternative, more simple writing of that. Of course it's snock rather than con, so of course the massive confusion is in like the use of cons rather than snock, but whatever. I would call it like cache.append or something. Anyway, so I think I'm pretty sure that all this does is just add it onto the end, because it's not a very like complicated function. So this is something that adds a base layer to the cache. So like appends something, cons something onto the end of the cache. Okay, that's fine. Cool. Build layer. Compute the next layer of the Merkle tree. Right. So we have n and m equals n plus 1. Cool. Leaves is a vector of length. Here, let me make this more readable. Leaves is a vector of length 2 to the m. And so basically this is an oracle computation that gives us a vector, right. Yes, so m is n plus 1. So we have the vector of length n plus 1, and now we're getting the vector of length n. And presumably this is by pairing, and yeah, so pair up the leaves and then hash each pair. So let leaves equal this. So this is this is, okay, it's using do notation, but we have the let statement here. So let the leaves be this this by rewrite at leaves. So basically this is like casting. This is a fancy way of saying, okay, we're just casting this this value to have the right like type. Rather than like 2 to the n plus 1, it's 2 to the n times 2. Pair up the leaves to form pairs. Pairs equals list vector alpha times alpha, right? 2 to the n of function leaves.get. Right, so we're just indexing into leaves. That makes perfect sense to me. Cool. And then we hash each pair to get the next layer, and we of course have to use the query to do that. Let hashes equals list vector alpha list.vector m map. So this is like the monadic map. Great. So we're doing a whole bunch of, basically this is a fancy way of saying we're doing a whole bunch of query operations to get the output, and then we return the hashes. Cool. And then we build the full Merkle tree returning the cache. And we do this by saying, okay, we start with some leaves. Is this how this, like ideally one feels like there should not be two different natural numbers in the type signature of this. One feels like it should be something along the lines of, I give you a vector of length n, like I give you a vector of length 2 to the n, and you return a cache of order n. But I see there are saris in this, right? So build full Merkle tree. So I wonder if I can, like, let me see if I can, like, write the thing that I'm describing. So build full Merkle tree prime of order n. I have something of order 2 to the n, and I'm not doing the plus 1 here. So I have the leaves, and I'm trying to get this oracle computation. But I can run an oracle computation, right? So what I think I want, like, is it possible within this, like, do notation to, like, case on n? Or, like, match n with 0. Yeah, so what is actually going on here? So the point is that if n is of length 0, then I simply have, right, let's try and fill in this first, right? So if n is equal to 0, what I have is that maybe I can like sorry this out as well. This is, yeah, this is like a weird, is this like some bug in how it's rendering? If I put my cursor immediately before the sorry, I indeed see the zeros here, which is what I expect. But if I put it here, I see n's. I feel like that's gotta be some kind of problem. Okay, but let me see if I can like write what I think should be the right answer and get something to work here. Right, so I have a vector of length what? Of length 2 to the power 0, which is 1. So I have a single alpha leaf. And now I need to get a cache of order 0. A cache of order 0 is, of course, a single layer of length 1, right? So I just need to return that. Yeah, so it's like, it's close to what the AI was outputting a little bit earlier. What was the AI outputting a little bit earlier? Cache.cons does not, is cache.cons helpful here? I feel like it's not, right? So I need an oracle comp, right? I'm not going to use the oracle at all because I don't need to pair anything off. So what it feels like I should simply do is, if I have n equals 0, right? So like cache, what do I need? I need an oracle comp. Like what is, okay, I need to like think more. It's, yeah, so I'm within the monad. Am I not like within the monad here? Like I need to return an oracle comp, but I'm within do notation. So I really just need to like return a cache, right? Return something. And this is the cache that I need to return, yes. So what is a cache? Right, a cache of order 0 is a function, right? It's a function from j to j is of course just literally 0, and so it's not actually relevant here. Right, val. So I need, so really I just need this to be like leaves, right? It just needs to be the actual literal leaf. Type mismatch, right? And this is where like this sort of weird thing happened, right? Where we were rewriting with J, right? So like I can maybe like do like a by notation here, like by simp at J. So J is just fin1, right? Have J. Have J.val equals 0. Rewrite this. Exact leaves. And it's all happy, right? I wonder if this can be made like inexact, just so that it's a little more clear. Yeah, fin val equals 0j. By exact fin val equals 0j. And so this can usually be done like this. And in fact, this can usually be done like this. And then this line could be, and I can like reconstruct this to by rewrite at. Is that possible? Okay, so I mean, that seems roughly correct though. So I just want it to be the leaves in the case where like it has to be I have to reference the leaves somehow. So yeah, I think this is just correct. And so now we're in the n+1 case. And again, I can see the proper thing if I look at sorry. But now I want to invoke build layer recursively. I want to invoke build layer recursively. I want to invoke build Merkle tree prime recursively, and then invoke build layer. All right, this is where I question, like, why can't there be a build layer prime where the types are right? Let me like try and copy this out. What happens if I just do this, call it build layer prime? There's no m. M is equal to n+1. M is equal to n+1. Unknown identifier h. Don't need to rewrite with h. It's just all goes through. Right, so that's build layer. And so now like, okay, build layer prime looks a little bit more lean-like. And so yeah, let me not forget the type. So I have a list of length 2 to the n+1. Build layer lets me take a list of length 2 to the n+1 and get a vector of length 2 to the n, the pairs. So I need to, yeah, so once I have the pairs though, yeah, that would then be a vector of length 2 to the n, to which I can recursively apply build Merkle trees. So so let's see, let last layer, build layer an leaves, application type mismatch for build Merkle tree prime. Sorry, what is build Merkle tree prime? Alpha is a type. Yeah, what's the complaint? The point is that it's supposed to have alpha. What happens if I make it explicit? Okay, so like making it explicit makes it work. Get cache. And what I'm supposed to return is an oracle comp of n+1. So I have a cache of n, and I need the oracle comp for the cache of n+1. So I think for that, I need the cons, right? Right, so from the last layer, I build the cache. And once I built the cache, I can cons. So this is the home stretch here. Return cache.cons this. Comment this out. Yeah, okay, cool. I think that's correct. Let me just look at this. Right, I get the last layer from the leaves, right? Like you can think of the leaves, right? You can think of the layer above the leaves as the like last layer of the tree proper. I build the cache from the last layer, and then I cons on the leaves to the cache, or the, build Merkle tree. 2 to the n, something ending, right, yeah, so the order, right, the index into this tuple is fin n plus 1. So the biggest element is n, and the biggest row is 2 to the n. So the leaves should be in the cache that it returns. The cache has the last layer, and then I return by consing on the leaves to the cache. I think this is all correct. And I think that this, and I think I like my version better of like without the like redundant m. So I think I'm gonna, I don't know, maybe delete and pull request this. I don't know, we'll see. Like, presumably if I delete all this, it will reinterpret it. Git will reinterpret it as like some changes. So this, and I'm also going to delete the primes, and delete the primes here, and delete the primes here, delete the primes here. Do I really need this A? Yeah, that's, I don't know how that's supposed to work. I guess I don't need the like type description because it already knows that alpha is type, but I guess it's just too dumb to know that alpha is already in the type. And I can delete all of this. Okay, build the full Merkle tree, returning the cache. Get the root of the Merkle tree. Yeah, so I can get cache 0 get. Yes, cool. That's a cool way of getting the root. Cool. I believe that. Find neighbors. Figure out the indices of the Merkle tree nodes that are needed to recompute the root from the given leaf. Right. Yes, so this is like finding the whole branch. Figure out the indices of the Merkle tree nodes that are needed to recompute the root. So basically we're given we're given n. N is the order of the tree. I is a particular index of a leaf of the tree, or an index of the last layer of the tree, however you want to think about it. And what I want is, given an index into the layers, like what would be helpful here, maybe I can like additionally like, here's what I'm actually going to do, right? I'm going to make it a little easier to read all of this by renaming this to layer. Renaming this J variable to layer, right? Layer index into a layer.value. Okay, wait, sorry, is that correct? J. I'm just gonna like very carefully make sure that I do this right. Cache.cons, reverse induction leaves, and then the function, right, that takes a particular layer and gives us the cache at that layer. So I think this is right, layer. Right, so if I have a cache, the argument that I call the cache with is a layer. Yeah. And then I have the leaves. I could even like go one step further and call this the depth. I could call n the depth. Right, so for a depth n tree, it would have 3 layers. Does that make sense, right? Like a Merkle tree with 3 layers is a depth 3 Merkle tree. I think that makes sense. Of course, this has the disadvantage of not being a single variable or a single character variable name, and so it becomes more verbose. This is also the depth. And this doesn't need to be in parentheses. Let me think about that again, right? If I have a depth 0 Merkle tree, that would have 1 layer. That's a little counterintuitive. Maybe I like revert these depth changes. I'm just gonna like let that continue to be called n. Okay, that's fine though. Okay, so I can get the root and I can find neighbors. So this is going to return me a tuple. Okay, so I can continue. This is a layers though, right? So this is a function from a layer called an n to layer.val. This line exceeds the 100-character limit. This is also technically written in bad style because like this should really just be a part of this function, right? Fin function finequiv infun give the little endian order 6 equals 0, 1, 1. So we need to reverse to get the big endian order. Bits vector of fun fin function finequiv inf fun I. Right. Yes. Yes. Okay. So this is like the equivalence between functions. Yes. Yes. The full power of like algebraic types. This is what they mean when they say algebraic types, right? Like functions are just like exponentiation. Okay. Yes, but we reverse some bits. Okay, I basically believe all of this is correct, except that I want to change the J. Fun layer. Let me change some style here. Something a little bit more readable. I remove this, and now all the J's become layers. Get root trivial. Can I just uncomment this, perhaps? What is this? Automatically included section variables unused in theorem. What is this? What is this? I've never seen this linter message before. Automatically included section variables unused in theorem get root trivial. Section variables, right? So I have variables for... Okay, so I think what it's saying that the decidable eq, inhabited, and fin type are not necessary for this theorem. I wonder if I can make this simply right. Get root. Yeah, not super easy to parse what this simp is doing, but I guess we're just like definition of get root. If I build a Merkle tree from a single, yes. So if I build a Merkle tree from a single value, the root is that value. Cool, because I never evaluate the hash function. And we also have another theorem here. Type mismatch query. Yeah, so this theorem is saying that if I build a Merkle tree out of two values, list. The list syntax is a little weird. I guess it's a vector. I guess the point is that it's a vector. Just a sec. Build Merkle tree. Takes alpha, n, and a vector. I thought there was like a notation for, like, can't I just say, for example, this? Is this not the type for, this is a type for an array. Is there not like a, yeah. Okay, maybe I'm just wrong. Maybe there's no type for vectors. There's no like notation for vectors. Well, let me just check that. Vector. No, there's this syntax. Okay, so let's see. Let's see if I can write this syntax. Pound v a has type root vector, but is expected to have list vector. Well, okay. Obviously, the problem is that it's confused about like the type of the result. Like this is proving that 1 is equal to 2 to the power 0. So that's fine. Okay, sure. And what do we have here exactly? Okay, so again, we have this, but what we're saying is that if we build Merkle tree, then the resulting Oracle spec domain is query AB Well, there needs to be a return type too, right? I guess query AB covers that because it's type mismatch. What's the type mismatch? Query AB. Argument AB has type AA, but is expected to have type, right? Get root. So I need to like return something. Query has type Oracle query. Okay, there's actually like, so the spec is Oracle spec A. What happens if I like copy out the full type? Yeah, that's a little weird. Why can't it infer that type? Okay, nevertheless, it gets it correct. Okay, cool. So this is just some theorem about single, and it has some like deprecated. Okay, generate proof. What is this? Generate a Merkle proof that given, okay, what is this? Given a leaf at index I is in the Merkle tree. That a given leaf at index I, right, so the proof consists of the Merkle tree nodes that are needed to recompute the root from the given leaf. So generate proof, right? So I'm given an order for the tree, an index into the tree, the cache, which is the contents of the tree, right? And yeah, so this tells me all I need to know about what the element it is, right? So like I can find the element itself by looking in the cache at the last layer at the proper index. And now I need to generate the proof. Just because I'm going crazy. Put in layer everywhere. Right, so this is how we generate a proof, right? We get the neighbors, right? So this is a vector of some kind. It's a tuple of, right? It's a tuple of locations within each layer, right? For each layer, there's a location. And then I get a function, right? So for each of those layers, I'm going to get the complement index at that layer, right? And the proof is, right? So the proof, right, consists of all the complements. And I guess not the value itself. Let me think about that, right? It doesn't, the proof actually doesn't include the value itself. I guess that's considered to be an auxiliary piece of data. So now I can verify that a proof is correct. So cool. So here's an Oracle computation that like, you know, permits failure. So I'm going to have to fail potentially. So I verify the Merkle proof. Verify a Merkle proof space that a given leaf at index I is in the Merkle tree with a given root. Yeah, makes sense to me. Given root. Yeah, so this is a particular leaf. This is the root of the tree. This is the proof. Yes. And so one thing that I have to do is I have to construct, right? I have to construct whether each time I'm on the left side or the right side that I'm adding the thing that I'm hashing, right? If, right, if n equals 0, then when we are at the root, just check whether leaf is equal to the root. Return leaf equals root. Else, get the sign bit of I. The sign bit is this. Show that I2 is in fin this. Let I equals I val over 2. If sign bit is 0, then it is the left child, and we let the new leaf be the query of the, right, so we get the new leaf, which is the leaf and the proof, the n-1th element of the proof. Otherwise, we get the n-1th element of the proof. And we put that on the left side of the hash. And then so we have to verify the proof recursively. Shouldn't there be some sort of equality check? Let me think about this. Right, so like to verify the proof, we do a bunch of Oracle computations. Then return, so no, yeah, the equality check is here, where we check that the leaf is equal to the root. Yeah, cool. It's just a little weird that it's a equals rather than an equals. I wonder if that's like going to cause a problem somehow. What happens if I just insert an equals here? Nothing else changes. Interesting. Okay. So now I have like completeness and soundness theorems. Comment this. Ooh, overloaded errors. I've never seen this. What is this? Unknown identifier n. Maybe I can do this. Ambiguous, two possible interpretations. Interesting. Well, I believe we've been using list vector everywhere else, right? Yeah, so. verify, yeah, so verify Merkle proof, I leaf, create Merkle proof, I cache. Let me think about this actually. Completeness. I verify the Merkle proof. I verify a Merkle proof that has been created, honestly. Even that's not quite right. Let me think a little bit more. So this should clearly be verify proof. But something's not right, because how did I get this cache? Application type mismatch. Fragment is type this. Unknown identifier leaf. Unknown identifier create Merkle proof. Yeah, so none of these things have been defined. So here's the point. I feel that there needs to be more like arguments here in the right. So I have n. I have a list of leaves, and I have the index of the leaf that I'm going to create the proof for. So like the first thing I need to do is like let cache equals build Merkle tree a leaves. Let proof equals generate proof, and I cache application type mismatch. Sorry, generate proof. Okay, whatever. Alpha. Do I want to be describing this whole thing as an Oracle computation? Do I want to be doing something like enclose all this in a block, do let cache equals this, let proof get the cache, return. Right, it just returns a bool, which is the pure true. Okay, wait, why can't I use cache here? Cache has type Oracle comp. So build Merkle tree. So it gets me a cache within Oracle comp. So I guess this has to be like this as well. Type mismatch. Now what's the problem? This type list vector. Okay, cache is a cache. Generate proof. No, generate proof is non-monadic. So this should be like this. Okay, so I have it mixed up. So yeah, I build the Merkle tree as an Oracle computation. Then I have the proof. Then I can generate the proof. Then I verify proof, which involves I, the leaf, the root. I also have to compute the root. Get root cache. That root equals get root cache. And then there's also like get the leaf, right? There's so I build the cache, I get the root. The root is the get root of the cache, right? I build the cache honestly using build Merkle tree. I get the root, I get the proof. I can also get the leaf somehow. The leaf really should just be leaves I. Let leaf equals leaves.getI, sure. Then I generate the proof, and then I verify the proof. Verify proof, and presumably I also need like alpha or something. Alpha, I, leaf, root, proof. Okay, like presumably it was previously called create, but this is just proof. Verify proof has type or okay, maybe I just need to do this. Yeah. Okay, interesting. And this feels like the right type, right? It feels like the right type because it type checks, but is it the right type? See, the thing that's making me feel weird about it is like I sort of thought that like an Oracle computation like references the Oracle queries that it makes. And so, right, so doing all of this and querying things multiple times is not exactly the same as simply returning true. Although, of course, the idea is that if you like interpret the computation as like just using the queries, then it's the same. Right, this actually looks correct. So this is actually what I like typed above. Build layer has already been declared. Can I verify that all of this is correct? Yeah, maybe not. Type. Yeah, I guess not. Interesting. Okay. right? Like even if I were just like isolating this from the monad and passing in the cache that way, I would still feel like verify proof like does queries. I wonder if this is like true. Let me see if I can like isolate that, whether it's true or something. Yeah, so induction n would be natural. H, something like this. Apparently this has to be like 0, I think. Sorry. Here I will put sorry as well. Right, so is there something like uses a vector, right? Vector dot, or it's like list dot vector dot head. Sorry, is it a list vector? List vector, yeah. So is there some theorem about like the head of a list vector being get 0? Like have I equals 0 by omega. Rewrite this. Simp. No goals. Great. Oop. Let me try and get the right thing. No goals to be solved. The simp value that I needed is vector.get0. And I think we consider it likely that this is how I can do this, and so I can maybe even do this and delete that, and maybe even just do like simp of that. No goal to be solved. Okay, apparently I do need some simp calls. But this is probably all I need in terms of simp. So this is like the easy case. And it would make sense that this would work because there wouldn't be any queries, right? But like this doesn't really resolve my concern. So the question is, can I prove the inductive hypothesis, or the inductive step? So if I do simp, I'm told that I have to, okay, wait, what? Max recursion. Right, there exists X, what am I being told? There's a cache AN plus 1. Such that build Merkle tree equals pure X, verify proof alpha I. What exactly is the type of X here? Right, it's a cache of n plus 1. Before this, cache was n plus 1. Bind equals pure if there exists. So I just have to find the value of the cache, I guess. Yeah, because all of these are let statements. Right, so I mean, clearly the value of the cache is the build Merkle tree. But here I have to find it without like access to the oracle, which gives me pause. So I don't know if I've actually done this right. How did it look before I screwed everything up? Right, it was just create Merkle proof cache, but it doesn't have any didn't have any like way of getting the oracle there either. Yeah, so I'm not even necessarily sure how one properly states the completeness. I think like one aspect is that it, right, bind equals pure if, right? So it was pure true. And I'm saying that there exists a cache such that build Merkle tree. There exists a cache, which is a non-monadic cache. So I don't think this is right. I don't think this is stated correctly. I think that perhaps the culprit is like calling this pure true. So I'm a little bit skeptical that I know how to do that. Clearly the completeness should be expressed as a statement about like whatever oracle you care to choose. It turns out to be complete. Yeah. Interesting. Okay, well, I'm just gonna like undo this because I don't think this is right. But I'm not gonna undo everything. So what did I like change here? Okay, I like added a space. And here I changed it to layer. Okay, it's all fine. This is unnecessary parentheses. So it's complaining that these variables are not like needed in for this theorem. So I guess the point is that I could put like a section, and then I could put an end here, and then I could put a section here. I could put the variables back, except that I want it to be these variables. Then I would end this section here. So that causes the linter to cease to complain. Yeah, it's interesting that like why are any of these needed? Why are any of these needed? Excellent question. Like fin type, for example. What is actually the necessity of doing fin type? Like one would think that where it would really start to become necessary is when you go to define the soundness and you want to start saying something like, oh, okay, we're uniformly sampling. We're making a statement that we're uniformly sampling over the space of oracles. And now I need everything to be finite, so that makes sense. And presumably decidable equality is needed because I'm doing some like comparison. Like here, like I'm doing this comparison. Okay. What did I change here? Right, so like the main thing that I changed here was this implementing the build Merkle tree in terms of this, as opposed to what it was before, which was build Merkle tree using both of these. And there was some sort of like, there were some sorries in it. Okay, so maybe I'll just make a pull request for this Merkle tree. Okay, so I've made changes, but I don't want to do them on this branch. What I want to go is go back to main. I want to take Merkle tree, and now I want to say that I'm making a new branch. And I'll just call this build Merkle tree. Create the new branch. Go, so this is present, and I say like really, I'm not implementing it, I'm really just sort of removing the sorries, but okay, so those are staged changes, so let's just commit those and publish the branch. I want to publish it to Bolton Bailey because I don't have push access to the other one. And the little thing is going to spin around and around. Okay, cool. Now if I go here, compare and pull request. Sorry, build Merkle tree. was playing around the library today. Saw there were some stories in this file. So I some things around to get an unsorried version of the build Merkle tree def. Named variable to is a bit more readable to me. That's helpful. You'll wait to tell me to revert it. Or ignore this PR. Create pull request. Okay, interesting. Well, this was fun. Take care for now.